Now let's look at an example. Actually, we're going to look at two examples where we can actually demonstrate the stability of an equilibrium by so-called constructing a diagram of null lines or loci. So here is the procedure. Let's look at our first example. Okay. So we are going to first sketch the coordinate system over here we have. Or let's try to remember the equilibrium. That's it for the first one. We have x star and y star, which is 19,020. One thing to remember is that we don't have to sketch a diagram to the scale. We can just say, this is just an illustration, not real. Okay. But roughly we're going to see the diagram. So this is x and this is y. So now we need to graph these two functions. One is called f of x, y is equal to 0. This is called a null line or a locus. In economics, we usually say it's locus, and in mathematics, it's called null line. And we know what it means. If capital F is equal to 0, that means x prime of x equal to 0. That means in x direction, the velocity is 0. So let's look at what kind of curve usually, but here we have a straight line. 50y minus 1 minus 0.05x is equal to 0. We want to see how it looks like. So we have 50y minus 1 is equal to 0.05x. And then we have y minus 1 is equal to 0.05 over 50x. And then we have y is equal to 0.05 over 50x and plus 1. So we have the intercept on the y-axis is 1, and the slope is positive, but it's very slow, very small. So this is something we have. This is over here is 1, and then we have a positive slope straight line. And this is the null line for f of x, y is equal to 0. We can write down this is x prime of t is equal to 0. Okay. Now we have another one. We have the second one, g of x, y equal to 0. That means 0.1y minus 2 equal to 0. We have y is equal to 20. So it's just a horizontal line, so like this. And this over here is 20. And this point over here has to be 19,000. And the intersection is the equilibrium. Now, after we have finished drawing the null lines, now we're going to plot these so-called short line segments. First, we can look at what's on each line. On this horizontal line, y prime of t is equal to 0. That means in y direction there is no velocity, and we only have x direction velocity. So that means tangent lines are going to flat, so it looks like this. Okay. These line segments indicate how the values is going to change along this line. Do the same thing on the other line. Since horizontal derivative is going to be 0, so if you think about the particle, it has to move vertically. So here we have only vertical line segments. Okay. After we finish this, we are now going to add directions, so-called arrows. Let's look at the vertical ones over here. This point over here is 20. So for values above this line, y is bigger than 20. If y is bigger than 20, then y prime of t over here is positive. So here, y prime of t is positive, and beneath this line, y prime of t is negative. that means we have arrows pointing upward because y is bigger than 20 and the derivative is bigger than 0. And beneath 20 it's going to be negative. So, and we added these arrows over there. And do the same thing for the short line segments on the horizontal line. We are determining whether it's going left or going right. And the equation we're going to look at is the one for x prime of t. So it's over here. And when x is large, it's negative. When x is small, it's positive because of the negative sign in front of x, or this 0.05, the coefficient. So we know when x is large, it's negative. That means x value is decreasing. X prime of x over here is negative. On this line with a small slope is 0. And when you cross this one, then the x prime is positive. So the value of x is increasing. So here you have x prime of t positive, so it's going this way. Now once we have these arrows, we can actually see the dynamics of the system. This point over here is equilibrium. It's not going to move if your value starts from over here. But if in this region, it's going to go left and up. If it's in this region, it's going to go left and down. And this region, right and down. And this region, right and up. So imagine you have an initial value, say over here. Then if you follow this trend, then it's going to look like this. It's going to go down like this. Okay. And if it's over here, then you have something like this. This is called each line over here represents a solution. Wherever you start, that's called initial value. And these two regions is pretty easy to do. But if it's over here, if the initial value is over here, what does the dynamics going to do to this point? It's going to push up and left, then it's going to cross. Once it's crossed, it's going to go other way. Okay. And the same thing happens over here. If you start with initial value over here, then it's going to go down, but it's going to cross this line, and then once it's crossed, it's over here. So now you will see this point over here is unstable because nearby solutions are going to leave this point. In fact, this one is called a saddle because you have this kind of behavior. Okay, you have this kind of behavior. It goes this way and this goes this way. It looks like a saddle. So here we have x star, y star. It's a saddle, and we can see it from this diagram. Alright, we're gonna try the other example in another segment.